Okay, so let's continue the analysis here. We're trying to analyze this toy example where we have two stations following a certain protocol and figure out what is the maximum load, what is the efficiency, and etc. for this scheme. First of all, if we want to calculate the effective data rate, that is the number of bits per second we can transmit, and now the bits are the bits that we get from the layer above us. So then we need to then first of all figure out the time it takes to transmit a frame, and then take the number of bits in the frame and then divide with that time. So, or more precisely, the time it takes between two frame transmissions. What is that? Okay, so the time between two frame transmissions, or rather the shortest time it can possibly be, let's call that t. That is the time it takes from initiating a coordination period until the next coordination period can start. Okay, so it's the time from here to here before we can start to transmit the next frame. Whether this one goes from A to B or B to A inconsequential at this point. Right? It takes this amount of time for doing this. Okay, and then if we calculate the times here, we see it's going to take 3 times t prop, 1, 2, 3, and then plus x. And x is the time it takes to transmit one frame. It used to be called tf before, maybe more descriptive, but now it's called x. So x is the time it takes to transmit the frame, and x itself is the length of the frame in bits divided by the bit rate, which is used to transmit the frame with. So t here, first of all, is 3t prop plus x, and x is L divided by R. So x here is the frame length, in seconds, and L is the frame length in bits. And R is the data rate of the medium. Okay, and when I say medium, I mean cable or whatever, right? Whatever we use in order to transmit the frame. Okay, so the effective data rate is then simply the ratio between the number of bits, useful bits that we are transmitting, and the time it takes to transmit those. So it's x divided by t. Sorry, it is L, the number of bits in a frame, divided by t, the time it takes to transmit the frame. Or rather, more accurately, the time it takes from initiating the frame transmission until the next frame transmission can be initiated. Right? Which is more than the time it takes to transmit the frame per se. Right? Okay, so what is then the maximum supported load we can have for this? Okay, so now we have calculated this effective rate. Now, if we want to calculate the maximum load we can use on this system, if the system is maximally loaded, that means that we are using it constantly for transmissions. Okay, so here we start to transmit one frame, and we immediately start to transmit the second frame, the third frame, and so forth. So we're generating one frame for each one frame every t seconds, where t is this time it takes to complete the transmission. Okay. Then we are constantly using the medium, right? Okay, so for maximum load, occurs when the lambda, okay, so what was lambda now? Well, lambda is the aggregated frame rate, okay? So it's the rate of frames which are generated by, in this case, by both A and B together. So whether it comes from A or comes from B, or every second comes from A or B, it doesn't really matter. What matters is the total number of frames which are generated per second. Okay, and the maximum load occurs when this rate is as high as it possibly can be for this protocol, and that is simply 1 over t. Okay. So that's the maximum number of frames we can generate and still be able to transmit them on time, right? We can buffer them, but then the buffer will overflow. So this is the maximum rate we can transmit with. Frames per second then. Okay. So then, okay. So we generate a frame every t seconds. Hence, rho max, which is the maximum load we can support here, is then lambda, where lambda is given by this, times the length of the frame. So these are the number of bits per second which are generated by the system in total from station A and B. These are the number of frames per second, and each frame carries L bits. So these are the number of bits per second. And then we divide through by the capacity of the medium, which was R. Okay, and lambda we know is 1 over t, so here we get L over t over R. Or L over RT. And then we see that L over T is actually the effective data rate that we could use. So this is equal to the effective data rate. That's L over T divided by R. Okay. So that's another way to calculate the load. The load could be the effective data rate divided by the data rate of the medium. This is what we call in ARQ lingo, we call that the efficiency of the protocol. Okay. Okay, so we continue here, and then what do we know about the effective rate in this case? Well, it's L divided by, let's see, I think I wiped this out. L divided by T, and that is simply L divided by X plus 3T prop. T is 3 t prop plus x. Okay, so we continue here and we write this as L divided by R and then x plus 3 propagation times. And then L divided by R is x. We can write this as x divided by x plus 3 t prop, or 1 divided by 1 plus 3 t prop over x. So what are we trying to calculate here? We're trying to calculate the maximum load that our system can support, our protocol can support. We know that the maximum load has to be less than 1. In our case, we see now clearly that it is less than 1. It's 1 over 1 plus this, and this is a positive number. So this here tells us how efficient our protocol will be. So when the propagation time increases, the efficiency goes down, right? However, if we increase x, the efficiency goes up, or the maximum load we can support. So this turns out to be an important parameter here, and that parameter will show up in one shape or another later on. So if we call that A, where A is t prop divided by x, or if one wants to rewrite it, it's R, the bit rate, times the time t prop divided by L, because x here is R, L divided by R. So either way you like to see it, it's fine. And we see that this is some type of delay bandwidth product, which is normalized with the length of the frame. So here we have a delay, t prop, divided by R, bit rate, so we sometimes call that bandwidth. So this is a delay bandwidth product, and we normalize that with L. And what is L? Well, L is the number of bits in the frame. Okay, questions so far? Okay, so just to recap what we have done, we talked a little bit about medium access control, and now here is a very specific example of a simple medium access protocol. We calculated the effective rate and then calculated the maximum load we could support here. And we see that the most we can do is to offer this ratio of the underlying medium's bit rate to the layer above us. Okay. So there is some loss here due to the need to coordinate station A and B's access to the channel. So what one simply wants to do, what one would like to do, is to have a protocol for which rho max is close to 1. Right? Because then it can handle very close to full capacity of the medium. It can coordinate the nodes in that sense. Okay, so this normalized delay bandwidth product, this A here, turns out to be a key parameter, not only in our toy example, but also in more generic settings. And the main so the delay bandwidth product normalized with the frame length is a key parameter. And the reason why that turns out to be a key parameter is that when we want to coordinate nodes or stations, A and B in this case, we need to use the medium in order to do that. Okay, so the medium properties is important here. And the medium properties comes with delay and the bandwidth it can support. Okay, so for a high data rate and long propagation delays, coordination will be problematic. Okay. So coordination, then we need to use the medium in order to do that, either very explicitly or implicitly. Coordination efficiency decreases then with increased normalized bandwidth product. We can say that basically in general. Another thing that we were talking about was this frame transfer delay. Now it's a little bit unfortunate that I used the same t as I used on the blackboard here. It's not exactly the same t. The transfer delay is the time from when the frame was ready to be transmitted, which happens at that time. Okay, so here is when station A, the protocol, the MAC protocol received service data unit from above, until it's delivered at the receiving end, and it's delivered. Oh, it actually turned out to be the same. Sorry, it actually being delivered at this point in time. Okay, so T was actually the same thing. Sorry for that. So T is T. Okay. So this is known as the transfer delay, the delay from when it was available to be transmitted until it got delivered. Okay. And typically for when we have many nodes that we want to coordinate, the transfer delay here is a random variable. So if one looks at the mean of it, the transfer delay, the mean of the transfer delay divided by the time it takes to transmit the frame. So x, what was that? X was this time. Okay. The smallest the transfer delay can be is x, of course, right? So suppose that it's actually the propagation delays are very small, then we can approach 1 here. Then, as we increase the load, okay, then transfer delays typically increases, and increases dramatically when we get close to the maximum supportable load by that protocol. The maximum supported load by that protocol here depends on A. So when A is increasing, we move to the left here. Okay, and typically we move up here also. Okay, so A is our enemy in a sense, or A is what we have to work with. Okay, that's given by the medium, and we need to do the best we can with that. So depending on what A is, we have different protocols that are different, has different advantages and disadvantages, just as we have several retransmission protocols for different situations. Okay, so transfer delay, typically a random variable. The frame transmission time is x, length, number of bits per frame divided by the bit rate of the medium. Transfer delay increases dramatically, typically, right? As the load increases, so we get close to rho max. So what is the load? Well, the load depends on how much data the nodes that are attached to the medium has to transmit. Okay. So for instance, if we have a gigabit of transfer rate R here, R is a gigabit, but we only generate 1 megabit of the traffic on that channel, the load is very low. Then we're down here. But when we're getting closer and closer to 1 gigabit, at some point we hit the maximum load we can support with this protocol, and then the transfer delay goes through the roof here. So a typical operating point would be a little bit to the left here, at least if we're concerned with delays. Okay? So now we have talked a little bit on a toy example, a little bit about the general problems we are facing with medium access. So now step into a practical protocol to see how this can be solved. So this protocol here is a part of the family of random access protocols, and we will see how the randomness comes into the play here. And it's called ALOA. And ALOA does not stand for any fancy acronym. It's actually the indigenous language of the Hawaiian islands, and it's like hello in that. And the reason why it's called ALOA was invented by a person who worked at the University of Hawaii way back. Rumor has it he moved there for surfing, but he was also interested in data communications. Okay, so he invented that protocol on his spare time between surfs, I guess. And it's the simplest thing you can imagine, right? So what do we have? The main problem is we have several nodes. In this case, it was radio nodes that were distributed on the Hawaiian islands, and they wanted to communicate with each other. If I remember correctly, it was via satellite. I don't know this. I don't remember this for a fact, but they were separated quite apart from each other, and they wanted to share this medium, radio channel. So ALOA is very simple to stop and wait ARQ. And so how does it work? Well, whenever a new frame arrives from the upper layer, what do? We transmit that. Okay? So the transmitter here is rather simple, right? It just, as soon as I get a frame, I transmit that, regardless. And if no acknowledgement arrives after a timeout, okay, I start a timeout just as I do in stop and wait. And if I don't hear anything from the receiver of the frame, then I wait a random time, a random back-off time as I've seen here. I will explain this more carefully later on, and then retransmit the frame. So I get the frame, I transmit that. If I don't hear an ACK, I wait a little while, random time, and then I retransmit again. If I don't hear anything, I wait another random time, I retransmit again, and I keep on going that until I get an acknowledgement. If I do, I get the next frame from above. Okay? So, and the reason why we had this random back-off is that if we don't have that, then we could have collisions that keep on going for indefinitely. So to see that, suppose we have 3 stations here, A, B, and C. Okay? And station A and C has a frame that needs to be transmitted to station B. Okay? Neither of them here know about the other's intentions, right? So that's the problem. So we don't have any type of coordination, some magical person behind the scenes here that can coordinate the transmissions. So at this point in time, station A got a request for transmitting a frame, the blue frame, and it transmits the blue frame during this time, and it takes some time before it arrives at station B. Station C here received a frame from its layer above a little bit earlier and transmits here, and there is a collision here. And let's assume that collisions here are always harmful. So station B cannot make out anything out of this signal. So, but the B does nothing, right? It cannot do anything. So after some time, station C's transmission times out, and it retransmits the frame if there is no back-off. And the same thing happens with B. And we see that this collision here keeps on going indefinitely. Right? So initial transmissions, if they collide, then there will be no ACK, there will be retransmissions. The retransmissions will be synchronized in a way that will be new collision, and this process keeps on going forever. So collisions at station B is repeated indefinitely. So what to do instead is the following. Then station C transmits, station A transmits, so same initial setting. After the timeout, station C tosses a coin or draw a random number to find a random waiting time or back-off time before it starts to retransmit the frame that was lost in the first transmission. Station A do the same thing, and we see that if the back-off time here are random in a way such that they are large enough in order to minimize the probability of a repeated transmission, then collisions will be resolved. Okay, so the key to this is to make this introduce these back-off times, and these are random from time to time. So repeated retransmissions have different back-off times, and back-off times are random also between stations. Okay, and the interval from the smallest to the maximum of this back-off time here is a trade-off. That's something that we choose in order to be large enough in order to avoid repeated collisions, but small enough to avoid long delays. Okay, because the delay here, transfer delay, depends on the timeout plus the back-off time, right? So we don't want the back-off time to be too large, but it cannot be too small because then we're coordinating collisions again. Then we get repeated collisions. So it's a trade-off. But anyways, if we have this random back-off times, then eventually packets will get through. Maybe not at the first retransmission, but then maybe at the second or third. Questions? Yes?
Doesn't the backup time have to be dependent on the size of the frame?
Okay, so the back of time will depend on the size of the frame also, yes, right. So it has to, I mean, it cannot be too small because then nothing really happens. Then even the maximum spread between the back of times, there will still be a collision at B if these are large enough. Yeah, so that's right. So that's something, and a third factor to take into account. Okay? So what is then, if we would like to calculate the efficiency, maximum load, and all these things from this, how are we going to do that? Well, it turns out that analysis here is not so easy. Okay, so it's quite complex. It could be quite complex. So what I'm going to show now is a number of very simplifying steps that at the end of the day gets us to the right answer. Okay, so here's a instance of me hand waving a lot, and then the final equation is okay. Trust me on that, right? But don't trust what what I'm saying now is not completely accurate in all its smaller details. But if one went through it much more accurately, we would arrive at the same result. Okay, so what we want to do then is to first to say something about the efficiency when we have more than 2 nodes. Okay, we want to support many nodes. And to make actually our life a little bit easier, we want to support infinitely many nodes. Okay, because that makes the math a little bit easier. And then we also have to say something about with the rate that the different nodes are generating frames. So, in a way, how often does node C get a new frame to transmit? Okay, that tells us something about the frame generation rate for C, for B, and for A. And all of them together gives us the total rate on the system. Okay. So what we want to do is that we would like to model the frame generation somehow. Okay. And the standard approach to this is to say that we will think of that data traffic is following a Poisson distribution or Poisson traffic. Okay. So these Poisson random variables are usually often used to model the number of independent events that occur during a certain time. Okay, so this is not only for data traffic analysis here, it could be for many different things. So for instance, the number of people in queue for lunch at Linsen could be modeled as a Poisson distributed random variable. So if you go there will be different number of people in line, but if one did statistics on that, one would arrive to that they follow approximately a Poisson distribution. Okay, so other things could be the number of requests for a document at the web server, that typically a Poisson, could be a Poisson, or the number of frames, frame transmission requests. So we're going to use that one. Okay, so what is meant by this? Okay, so now if we look at the station, take station number 1 and look at what's happening during time. Then at certain times, station number 1 will receive a frame to be transmitted. And this will happen then at certain times. So here, for instance, a frame transmission request was done. So a frame transmission request was done at this point in time. And then it will take some time until the next frame will be ready for transmission from station number 1. And here, typically, when it comes to data traffic, this is not a regular flow of packets like this. It could vary a little bit the time between packets here. So the next frame might arrive here, and then the third frame comes a little bit quicker, and then the fourth frame is a little bit longer like this. So it's randomly distributed events here. Now, the time between these two events, two adjacent events, it's called the inter-arrival time. So the time between these two events is called the inter-arrival time. You can think of it as queues, right? It's the arrival of customers. Here one customer came, here's the second customer, third customer, and so forth. Here is frames. So first frame here, second frame, third, and fourth, and so on. So the time between these, the inter-arrival time, we model that as a random variable. And we model them as independent, identically distributed random variables. Okay, and we assume that the distribution for the inter-arrival times is an exponential distribution. So this time, the PDF of that is the PDF on an exponential distribution with parameter lambda. So the probability density function is lambda e to the minus lambda u. Okay, like this. For u greater or equal to 0, and it's 0 otherwise. So the probability density function is just a decaying exponential like this. And it's 0 for u less than 0. Okay. It turns out that the expected value of u is 1 over lambda. We did not, it's not u, let's call it z maybe. Okay, so the random variable z is 1 over u.
Sorry? What is the probability that we want to calculate?
What is the probability we want to calculate here? We just want to characterize how these could be distributed in time. So when it's like this, it means that for lower inter-arrival times are more likely than higher inter-arrival times. So we cannot say that, so if we want to calculate the probability that it's between these two things, we just integrate over this region here. Right. Oh. It should be not 1 over lambda, it should be equal to lambda here. Sorry. Okay. Now, the average number of events that occur during a certain time here depends on this lambda parameter. So the lambda is sometimes called the intensity. So we can interpret it, in our case, we can interpret lambda as the average number of frames that are generated during some time interval. That time interval could be second or minutes or whatever time unit we would like to say. So we can specify lambda as the number of frames per second, say, or the number of frames per minute or whatever, right? We will typically think of lambda as the number of frames which are generated during a time period x, okay? So the time period x here. So we will normalize with the frame length when we talk about lambda. Okay, that's just for convenience. Okay. Now, the number of events that occur during this time period, whatever time period we are considering, so let's call it time unit, is a Poisson distributed random variable. Okay. So if we call the number of events, let's call it capital Y. Capital Y is a random variable. So think of it as that we take our time unit, whatever it is, and then take a time interval here, and then just simply count the number of arrivals we have during that time interval. Okay, sometimes it's 0, sometimes it's 1, sometimes it's 3, maybe it's 16 sometimes. It varies, right? And then one can actually calculate the probability density function for that, and that's a Poisson distributed random variable. So the probability mass function for Y evaluated at k, so this is the probability that Y is equal to k. That is, it was exactly k frames that arrived during one time unit here. Then this is a Poisson distributed random variable. So, okay. So what is that function? It is lambda raised to the power of k divided by k factorial e to the negative lambda for k equals 0, 1, 2, etc. And it's 0 otherwise. Okay. So to recap, we model the data, the frames that are generated from a station as a Poisson data traffic, which means that the time between two frame arrivals is an exponential random variable, which is then characterized by this factor lambda, which is known as the intensity of this one. When lambda is large, the time between arrivals is small. Okay, so intensity is how fast we get frames. If we want to calculate the total number of frames which are generated during a time unit, we call that Y. That turns out to be, under these conditions, a Poisson distributed random variable. It's not obvious that that will be the case, right? But it is. Trust me on that one. Okay, and it has this probability mass function. So for this one, I can calculate exactly what is the probability that we get 3 new frames during a time interval by just putting k equals to 3 and evaluating that probability. Okay. So what does this help me? Well, it helps me in the following way, because Poisson, now we have characterized the data traffic from one station. Now, what we would like to do is to characterize this also for the second station, third, and so forth, and then pool everything together to say what is the total system data rate or frame rates which are generated. And then Poisson distributed random variables has this very nice property, is that if we add 2 flows which has Poisson distributed data traffic, the sum traffic is also Poisson distributed. So it's almost like Gaussians. When you take 2 Gaussian random variables, you add them together, you get a new Gaussian with new variance and mean, but it's still a Gaussian. Okay. So for this case, here is the PDF of a Poisson distributed random variables. And if we have two Poisson distributed random variables, z and y, with different intensities possibly, when we add them together to form W, what we get is a Poisson with the sum intensity. So it's quite natural or it's a nice equation, right? And that would certainly not be the case for any other distribution here, right? But for this one it is. Okay, so why is this useful? Because now if we do some simplifying assumptions on ALOA, that all frames have exactly the same time duration, x, that during x seconds, so x here will be our unit, our time unit that I talked about earlier here. So during x seconds, the number of new frames which are generated for transmission, let's call them y, it has is Poisson with a certain intensity, lambda n. So we can think of lambda n as new arrivals from above for all stations, okay, new frames to be transmitted. Now we also have frames that needs to be retransmitted, those who are in backoff here. Then we assume that the backoff is such that we can model retransmissions as also Poisson distributed data traffic. Okay, so the number of old frames that are scheduled for retransmissions, we think of them as z, as some Poisson distributed random variable with some other intensity lambda r. Then we think of y and z as being independent. Okay, so that's also a simplifying assumption. Then the total rate, which we need to transmit with, or the total rate of frames that arrive during x seconds, is y plus z. Okay? Y new frames and z frames which are scheduled for retransmission. And that happens to then be Poisson with variable intensity g, where g is the sum of the intensities. Okay? So in a block diagram, we can think of here, y comes into the system. These are new frames. And then there are some frames which come through a backoff process. And the sum of new frames and backoff frames is the total frames that are coming to the system for transmission. So that goes through the channel. If there is a collision, then a bunch of frames are scheduled for backoff and will be returned for transmission some later time. But some of them might go through. Okay, so we have this feedback system here. So we all love control theory. So here's like a feedback system, right? So what we would like to do then is to then have this very simplifying assumption also that the propagation delay is 0. If the propagation delay was 0, we wouldn't have much of a problem. But let's assume that for the purpose of analysis. In practice, that means it's negligible compared to the frame length. And then we say, okay, we're going to have infinitely many frames, infinitely many stations, which means that the frame rate per station is very, very small. Otherwise, the system will be completely overloaded. Right? So we can think of it, we have billions of stations. All of them have maybe one frame to be transmitted during a year or something. Very low rate per station, but together a high rate. Potentially a high rate. Okay, and that means that whenever these new frames here, this rate will not be affected by the number of frames that are in backoff. That's the implication here. And why is this important? Well, if I'm a node and I get a frame from above to be transmitted, if I'm in backoff, I don't accept new nodes from above, and maybe that would affect the new frame arrival rates. Maybe this was more information that you needed, but that is actually the key assumption here. All right, so I'm going to skip the analysis here and just show you the end results, and we will do the analysis a little bit more next time we meet. But essentially what it ends up is like this. Okay, and on this axis here, we have the throughput, normalized throughput, and it can be at most 1. And here is the total rate that we are putting into the system. And what we would like to do is to maximize throughput. And if we're using ALOA, it turns out that we can support a normalized throughput of 1/2E, and E is this, 2.7 whatever, right, the natural number. So E turns up here magically. So about 20% of the total system data rate can be used for the higher layers. So the cost for coordinating using ALOA is that we can only get about 20% through. 80% is lost due to coordination. So it's not a very efficient protocol, but it's super simple, okay? So therefore sometimes used. And an improved version of this is when we use slotting, and then we can double this to 37%. But it's still not super great. It means that 60% of our frame transmissions are useless. Okay, but let's pick up the ball on this on Thursday. So see you then.